Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, here we go with our next lesson. We are going to focus on the process for changing fractions into percents. I think we've talked a little bit. I know in 6th grade you would have gotten some information about how to find equivalent fractions. And so in this case, we're going to be doing the exact same thing. We're going to multiply our fraction times a giant 1 to get an equivalent fraction. But in this case, it's a very specific equivalent fraction that we're going for. And so before we get into that, let's go ahead and take a look at what is the definition of a percent. Percent literally means out of 100 or divided by 100. So what our goal is if it's out of 100, you think of a fraction where you've got 100 in the denominator. Remember, the fraction bar also means divided by, so that fits in with this part of the definition. So percent literally means out of 100, but if you think about it as divided by 100, then hopefully you'll remember that you need to get that 100 in the denominator. So looking at, if we were to say, what is the percent, let's move you out of there, what percent would be the equivalent for the fraction 3/4? Okay, so if I'm thinking about that, I think, all right, well, 3/4 has an infinite number of equivalent fractions, right? 3/4 is the same as 6/8. If you multiplied it times 2 over 2, if you multiply it times 10 over 10, it would be 30 over 40. If you multiply it times 20 over 20, it would be 60 over 80. So we've got all these equivalent fractions. It turns out if you multiply the 3 times 25 and the 4 times 25, you'll get a fraction with a denominator of 100. And so 3/4 is the same as 75 out of 100, so therefore we can say it is equivalent to 75%. So our goal today is to take a look at the process of how and why we're able to, what we're doing basically when we convert a fraction to percent by changing it to an equivalent fraction out of 100. All right, so in the last few lessons, you've been working with fractions and percents to represent probabilities. In this lesson, you will use geometric strategies to further your understanding of how to convert fractions to percents and to model the conversion. Geometric strategy, I guess, is the CPM term for using manipulatives where you're drawing pictures of some kind. So yeah, you know how you can take rectangles and break them up into equal parts to represent fractions. If you shade in 2 of the 5 equal parts, how you're using a rectangle to illustrate a fraction concept, that's what we're talking about here. So learning geometric strategies will give you a deeper conceptual knowledge of the connections between these different representations of portions. So a lot of you are visual learners where just reading a paragraph, you may not remember everything you've read, but if you see a picture, sometimes you get that photographic memory where you can remember what the picture looks like, but you can't necessarily remember all the words in a paragraph. So just, different people learn different ways. CPM and this math program, they try and touch on as many different learning styles as possible to help you understand the concepts and learn the math. So to get started, let's take a look at Lorraine and her partner here. It says after 25 flips of a fair coin, they like to call it a fair coin instead of a coin. I don't know what an unfair coin is, but maybe the unfair coin has 2 heads or 2 tails. Either way. Lorraine and her partner recorded 14 heads. Okay, so out of 25, that's the number of flips. This is experimental probability. 14 of the time, heads came up. So the heads in this case is the desired outcome. So is this more than, less than, or equal to 50%? Okay, so you know that the theoretical probability of heads would be 1/2, right? So that's why we're comparing it to 50%. So go ahead and think about that. How do you feel about that? Is 14 out of 25 more than 50%? Is it less than 50%? Or is it the same as 50%? If you said that it was more than 50%, you would absolutely be correct. 14 out of 25 is more than 50%. Just remember that, fractions that are equal to 50%, the top number is always exactly 1/2 of whatever the lower number is. So if you had 10 out of 20, that would be 1/2 because 10 is half of 20. What number is half of 25? Isn't that 12.5? So any fraction that has a denominator of 25 and a numerator that's more than 12.5 is going to be more than 50%. And if it's less than 12.5, it would be less than 50%. So 14 is more than 12.5, so that means it's got to be more than 50%. So percentages are one way to compare different portions of a total. If you have not already done so, work with your partner to calculate what percentage of Lorraine's flips were heads. All right, so can you figure out 14 over 25, what percent is that equal to? See if you can figure that out, pause, and come back to me when you think you've got it. All right, so what I did here is using my giant 1, I converted 14 over 25 to 56 out of 100. We know that, we talked about it here, 12.5 out of 25 is 50%, and this is going to be less than 14. That makes sense, right? So 50% is going to be less than whatever this percent is, and it turns out that 4 times 25 is 100, so we have to multiply 4 times 14 to give us 56. Therefore, 14 out of 25 is 56%, and they flip the heads in this particular trial 56% of the time. Now, let's go back here for a second where it says percentages are one way to compare different portions of a total. You know how we've spent some time comparing fractions, like I did it right here, 12.5 over 25 is less than 14 over 25? Well, when you've got two fractions with different denominators, you've got to get a common denominator, right? It's sometimes complicated trying to figure out. Let me actually just throw in a random page here. If I said 171 over 283 and tried to compare that to 165 over 271, like, I don't know which one is greater. I mean, we can figure it out, but it's not obvious. So you've got to either figure out by converting both of them to decimals, both of them to percents, or both of them to fractions that have the same denominator. Now, if we choose to convert them to percents, essentially what we're doing is we're rewriting each one of these fractions with a common denominator of 100. That's what we're doing. And so whenever you have two fractions that have the same denominator, when you compare them, all you have to do is compare the numerators. That's what we would be doing with the percent. Technically, this would be 50 out of 100, and this would be 56 out of 100. So 50 is less than 56, so this one's got to be less, this one's got to be greater. So converting to percents is basically the same thing as just finding an equivalent fraction that has the same denominator as the other fraction you're comparing it to. That's what we're doing. All right, I'm not going to finish this. I hope you don't care. Okay, so what do we have going on here? Tamar also kept track of the number of heads he flipped. He wrote his experimental probability of flipping heads as 7 out of 20. So he flipped it 20 times, and 7 times heads came up. Not what we expected. It looks like less than we expected, right? That's going to be less than 50%. Now, let's look at his strategy for trying to figure out what this percent actually is. He wants to write it as a percent, and to do so, he knows that he needs to rewrite it so that the denominator is a 100, not a 20. So we started by drawing this picture at the right. So you see how why he drew this representation to show 7 out of 20. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 boxes are all the same size, and 7 out of those 20 are shaded in. So this is a visual, a geometric representation of the fraction 7 out of 20. Now, Tamar realized that he could adjust his drawing by showing it in 100 parts instead of 20. So essentially what he's done is he's going to take and he's going to draw some vertical lines in here, which is going to change it from 20 equal portions. See if I get that right. That looks pretty good. To 100 of them, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So he's got 10 columns now with 10 boxes in each column. So that's what he's got here. And to equally distribute, notice how you had these, you had these 5 random ones right there. So what he decided to do was break them apart into little chunks. So this was the squished in version of that, right? You've got 7 out of the 20 filled in, shaded in. So if you do this enough times, how many times would that be? 1, I guess I can't move that guy over. Looks like you're going to have 5 groupings of 20 there. Why do I have these guys there? I don't know why those are. So how many total parts are shaded in all of this? We've got a total of 35 parts that are shaded, right? So you got 10, 20, 30, 31, 32, 33, 34, 35. Now, if I bring this over, you still show that there's 35 out of 100 that have been shaded in, right? So what was the point of him drawing it this way and spacing them out? Well, Tamar wanted you to visualize that basically you took the 7 out of 20 here and you reproduced it 5 times. So you got 5 times the number of 7s, which would be 35, or 5 times the 7, and then 5 times the total, which is 20, to make a total of 100. So this is a representation of 35 out of 100 now. So we can conclude that 7/20 is equivalent to 35%. So you don't necessarily have to draw the picture to figure that out, but the visual is nice to see to show that what we did mathematically here actually works visually, geometrically as well. All right, so what we would like for you to do now is to do the exact same process, but with the fraction 3/10. So we want to rewrite it, show a visual where you can convert this 3 out of 10 to a number out of 100, and then count up the total number of shaded parts to determine what the percent actually is. So go ahead and pause the video, copy this down. I've already got us started here. And then what we want to do is we want to draw those vertical lines like we did up here to create a 100 box here instead of a box where there's 10 going across. And I know I've got my coordinate grid in there so you can see the vertical lines, but I'm going to go ahead and do that anyway. I'll pause my video. You go ahead and pause it as well to get yours drawn. And then when we come back, I'm not sure I cut myself off. When we come back, we'll have all 100 boxes in there. All right, so we started off with 3/10. Now we've drawn the vertical lines in here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 across, 10 down for 100 total squares. So how many total squares in there are shaded in? Well, essentially what we've just done is this. We've said we took a representation of 3/10 and we turned the 3 into 30 by breaking this into 10 equal parts. And we took 100 or the 10 and made it 100 by breaking that into 10 equal parts. So we've essentially changed 3/10 to 30 out of 100. Since 30 over 100 by definition is equal to 30%, that means that 3/10 must also be equivalent to 30%. Okay? So this right here, that's the process we use to convert from a fraction to a percent, essentially, by finding it as a number out of 100, and then the numerator becomes your percent. All right, this is an example of a stoplight problem. I think this is the first stoplight problem we've had in 7th grade so far, so I want to be clear with you. Stoplight problems are showing a very common mistake that students make. And if you can see the mistake, the common mistakes people make, and understand why they made the mistakes and what they were really supposed to do instead, That's a very powerful learning tool. So Randy's doing the double heads game, and this is kind of similar to that first one with Lorraine and her partner. He scored, well, I'll read it through. Randy was playing double heads, a game in which he would flip 2 coins at a time. He recorded the number of times that he flipped 2 heads at the same time. He did this 50 times, and 20 out of those 50 times, 2 heads came up. So 20 out of 50, how does that compare to 50%? Is that more than 50%, less than 50%, or is that equal? And if you look at the 50, it's like, okay, right, 50, half of 50 is 25, so doesn't this have to be less than 50%? And your answer, yes, it is less than 50%. So Randy is not in agreement. He says 20/50ths is equivalent to 70 over 100, because if I add 50 to the numerator to get 100, and I add 50 to, I'm sorry, if I add 50 to the denominator to get 100 and 50 to the numerator to get 70, then I'm going to get 70 over 100, right? He's like, remember that giant 1 thing? Take 50 over 50, and now we'll add them together, and we got 75 out of 100. Okay, there are a couple of mistakes here. First of all, the whole giant 1 idea is put into place because the number 1, whenever you multiply anything times 1, it's always going to be equal to itself, right? So when I take 25 times, wait, what did I do here? That was supposed to be the 20, and that was supposed to be the 70. Sorry, whatever. We'll come back. That's fixed. Whatever. Okay. So whenever you multiply anything times 1, it always is equal to the original number, right? And so by multiplying times a fraction that's equal to 1, you are converting the fraction to an equivalent fraction. You're not changing its value. That's one of the reasons why we call it a giant 1, is so you get that image of multiplying a number times 1 is always equal to itself. But when you add 1 to a number, that is not at all going to be equal to itself. It's going to be 1 more than that. So if I were to have done this problem like Randy said, then my answer would be 1 in 20/50ths, right? And that's more than 1. It's obviously not going to be equivalent to this number, this fraction, which is clearly less than 1. Okay, so common mistake. We do need to deal with a giant 1, but we're not adding it. We're supposed to be multiplying it times the original fraction. Clean things up a little bit. I was not very happy with my work there, so I just want to remove all of it. Okay, so let's go ahead and show this. So 20 out of 50 is less than 50%. It's actually 40%. And 70 out of 100 is greater than 50%. There's absolutely no way that they could be equal to each other. Okay, so that's yet another way of thinking about it. So go ahead and jot this down. To get equivalent fractions, you must multiply the numerator and denominator by the same number. And if we want to put that visual here, if you take 20 out of 50, what do you need to multiply times 50 to give you 100 so that we can declare it as a percent? That would be a 2, correct? So we're going to turn this into a giant 1 and multiply 20 times 2, and that will give you 40, okay? Numerator and denominator getting multiplied times the same number gives you an equivalent fraction. And in this case, we want the fraction with the denominator of 100, so we chose the number 2, since 50 times 2 is 100. All right, 3 students invented a game in which they flipped coins for 1 minute and then determined who flipped the highest percent of heads. After the first round, each of them thinks that they are the winner. Here is what they reported. You got Maria. She recorded 12 out of 25 were heads. You've got Autumn. She recorded that 18 out of the 40 were heads. And then there's Kumar, who just went straight to the percent. He's like, yeah, I know mine's 44%. I don't need to worry about the ratios. So I guess we have to compare all these to Kumar. If we're going to try and figure out who had the highest percentage of heads, then we've got to convert Maria's to a percent And we've got to convert Autumn's to a percent so that we can compare it to Kumar's 44%. Okay, so let's start with Maria. What do we have to do here? Maria's as a percent. Well, let's look at the denominator. What can you multiply times 25 to give you 100? We would multiply that times 4, correct? So thinking of the giant 1, you have to multiply the 12 times 4, and what do you get? 12 times 4 is 48, so that's going to be 48%. Taking a look at Autumn. This can be a little bit trickier. Autumn, if we want to multiply 40 times something to give us 100, what do you multiply times 40 to give you 100? You can figure it out just using your calculator, but sometimes if you can simplify a fraction, maybe you can find a friendlier denominator. So I'm going to do it both ways. I'm going to start off by writing 18 over 40 as 9 over 20. And now when you multiply 20 times 5, you get 100. So 9 times 5 is going to be 45, which makes this 45%. So it looks like Maria is the winner. She did 48%, followed by Autumn at 45%, and Kumar at 44%. I'm going to come back up to this one, and I'm going to do it a second way. This is the way most students will do it. They'll grab their calculator, and remember our fact families. 40 times something equals 100, so 100 divided by 40 will tell you what your multiplier for your giant 1 needs to be. So I'm going to take 100 and divide it by 40, and that gives me 2.5. So if I multiply the top number and the bottom number times 2.5, if I don't get 45, there's a major problem here. So here 2.5 is already in my calculator, so I'm just going to say times 18, and sure enough, we get 45. Okay, so multiple strategies to figure this out. I'll teach you some more strategies later in the year. Right now, let's just focus on these. You know, if you can simplify, make a friendlier denominator, great. If not, just grab your calculator, do the division, and use that answer to the division problem, 100 divided by 40, to give you your multiplier to multiply times 18. All right, so get to work. Copy down these 4 fractions, and your task is to convert them into percents, and you can use any strategy that you like. Come back when you're ready. Show as much work as you possibly can. Make sure when you are showing your work that you are proving that your answer is correct. I want you to treat every single one of these problems like you just bet your older brother or sister that you are correct and they are wrong. And you have to show them and prove them that you are right and they are wrong so that they will pay you whatever you won by winning the bet. Okay? Treat every single problem that you solve like that, where you've bet that it's correct and you've got to prove it. All right, so hopefully you've paused and you've come back. If you just don't understand it, if you just want to watch me demonstrate everything for you and you copy it down, that's fine. Eventually on the assessments, you're going to have to understand it. So try and make mistakes. If you do, that's fine. You just correct your mistakes and you treat it as a learning experience. How much time do we have? All right, we're almost there. So 13 out of 20. If I write it as 13 over 20 is equal to x over 100, then I decide what would you multiply times 20 to get 100? That would be 5. So 13 times 5 is 65, which means our answer is 65%. 7 over 10 is equivalent to some number out of 100. What would you multiply times 10 to give you 100? Yes, that is 10. So 7 times 10 is 70, which means our answer must be 70%. If 12 over 25 gives you some number over 100, what do you multiply times 25 to give you 100? That would be 4. So 12 times 4 will give you the percent. 48 out of 100 is 48%. All right, now is where we get into some trouble. If I just kept this problem the way it is, I'm going to actually work it over here. If I said 9 over 30 is equal to something over 100, a lot of times what students will do, they'll take 100 divide it by 30, and you get 3.3 repeated. So you're maybe doing this with paper and pencil, and you say, all right, I'm going to round that off to 3.3. So now you take 9 times 3.3, and you get 29.7%. But technically that's wrong because you rounded the 3.3 repeated. So it's not always in our best interest to do it this way, because you end up rounding things off and you end up getting a slightly inaccurate answer. So any chance that you get to where you can simplify that fraction, 9 over 30 is the same as 3 over 10. And now we're going to take 3 over 10 and multiply it times 10 over 10. The correct answer is technically 30%, not 29.7. So that 3/10 matters. You know, you want to be as accurate as you possibly can. Now let's go back to this problem. If I did take 100 and divided it by 30, you don't have to round it if you're using a calculator. You can actually leave that number in there and then multiply it times 9, and then it gives you the correct answer. So it is possible to multiply times a repeating decimal using your calculator. Let me show you again. 9 times 3 point, I'm just going to keep doing this until the calculator won't accept any new 3's there. And it's not going to give me 29.999999997. It knows what I'm trying to do, and it'll give me the answer. Okay, so later on in the year, I'm going to show you how to solve this using proportional reasoning, which will ensure that you always get the most accurate answer possible. But right now, we'll just focus on these few strategies. All right, so that takes care of today. Good luck on your homework, and you can bet we're going to be doing these kinds of conversions from fractions to decimals to percents throughout the year, because 7th grade math, this is like the big theme of 7th grade math, is working with these ratios and using proportional relationship to solve problems. All right, good luck. Take care. Bye.
Hey, feeling good, like I should.